Hi everybody. Hi everybody. Hi up here in the camera. Hi. And hi here on the microphone. Hello. Welcome to my ASMR channel where I am going to be teaching you machine learning, AI, and different types of kind of scientific topics like that. My YouTube channel is called Neural Net Naps. If you are interested in learning and having information presented to you in a very soft-spoken, gentle, peaceful, relaxing way, then this is the channel for you. If you're curious about artificial intelligence, neural networks, if you've used ChatGPT, and you have a healthy scientific curiosity on how it works, and you also want to enjoy some paper sounds, then this is the place for you. Okay, this is the place for you. So today we are going to be reading this paper called Attention is All You Need. Attention is all you need. Attention is all you need. And this is one of the first papers that introduced the modern transformer architecture. Transformer. And a transformer is the mechanism that ChatGPT works in, and most of your large language models that you interact with these days. I know ChatGPT and Anthropic has Claude, and I think Google has Gemini, and those are all different large language models, and they run on this transformer architecture. And today we are going to be diving into this paper, which was the first paper that kind of popularized this attention mechanism. Okay, so I am going to be assuming very little knowledge, and I'm going to be teaching you everything from as simple principles as I can. I don't know everything. I read this paper pretty thoroughly before I started. I printed it off for you guys, and I'm going to be explaining it to you. I also have this notebook here to help us, and I read through the paper already and made some detailed notes on it. So hopefully I'm able to break down the different processes within this paper. And there's going to be a lot of paper noises and a lot of really cool scientific mathematical things. I am going to assume some linear algebra knowledge. If you don't know about matrices and matrix multiplications, then you are going to have to maybe review that a little bit, because I do kind of need a base to work on. But if you have some basic mathematical knowledge, then let's dive into this paper. So, when you have a scientific paper, you start off by kind of reading the abstract first. And the abstract gives you an overview of the entire paper, including the methods, kind of a very brief description of the solution, the results, and really positions it and motivates it within the larger kind of scope of the problem that they're trying to solve. So let's read it. I also have here in my little compendium on transformers the abstract written up as well. So it reads: the dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. So in the first sentence, we are introduced to a whole bunch of different things. First is transduction models. What is a transduction model? Well, I kind of wrote it here. A transduction model transforms an input sequence of data to an output sequence. What does that mean? Well, what's a sequence? What's a data sequence? I write on my scrap paper. Well, For example, if I speak a sentence, my sentence is a sequence. If I say random words, they don't really make a sequence because the order doesn't matter and it doesn't really bring together a story, okay? So for example, if I say a bunch of words like cats, apple, pudding, house. I just said a bunch of random words. But it doesn't really have a meaning. But if I were to say, my house has 3 cats and we are making banana bread, then it has some kind of deeper meaning and that becomes a sequence. Now, that is kind of an input into your model. So we have some kind of sequence, which could be kind of text, either written text or, oh, you're not in the frame, or spoken text too. Another example of a sequence is maybe musical notes. So again, if I play an F, D, C sharp, and it doesn't necessarily make a song, well then that's probably not a sequence. But if I'm playing notes that make up an actual song, like Fleur de Lis or something like that, or another song, then that is a sequence. So we can say music might be a sequence. Maybe some kind of pixel values that represent an image could be a sequence. Because again, they kind of occur sequentially and the order matters, and it also encodes some kind of information. So let's say like an image is some kind of sequence data. And all of this gets put into the transduction model, okay? Transduction model. And it outputs another sequence. So what's an example of that with text? What's kind of a problem involving text, either speech or written text, that might require a transduction model? Well, for example, if we try to do a translation task, for example, we have input in a certain language, let's say English, and we want to translate it to another language, let's say French. Well, a translation task would be a transduction model because it would take in a sequence. It would process it in some way, and it would output another sequence, okay? Another example is, for example, music. If we have, let's say, a song, I think I used Fleur de Lis as an example, but it could be any song. Let's say it's played in like piano. So let's say I have a song played in piano and I input it into my transduction model. It can output it in another instrument. So for example, instead of being played on the piano, it could be the same song, but it would hear, our ears would, it would make it sound like it's being played on the guitar. So you can see this a lot in, they have those online like voice changers. You could put in a song like sung originally by Taylor Swift, and then it could process it, make it sound like Ariana Grande, for example, is singing it instead. So that's another example of a transduction model. So, that's kind of the idea of it. It takes in a sequence and it outputs a sequence. So, it says the dominant transduction models, what we talked about here, are based on complex, recurrent, or convolutional neural networks. So, anything that's a sequence, naturally, it makes sense to use recursion or a recurrent network. So what is a recurrent network? Well, a recurrent network is, this is kind of the basic shape of it. So we have some kind of hidden state, okay, H naught, that we start off. And let's say it takes kind of an input. I'll call it I naught. It's my first input. Maybe it has some other initialization. So I'm going to call it HI. This is kind of the some kind of initialization. So then it takes in some input and then it produces some output. So this can be the first, I'm going to call it out 0. And for example, if we're like translating, it would take in the first word of a sentence and it would output the first word of the sentence in the other language. If we were doing one of the music tasks, it would take in the first note, or maybe it would take in a group of notes, depending on how you tokenize it. And it would process it, and it would output the first note in kind of the other form, whether it sounds like it's being sung by another person or it sounds like it's coming from another instrument. So then it would take this hidden state and it would pass it on to the next hidden state, which is called H1. So you see this kind of subscript represents the time component. And it would take another input, H1, and it would produce another output, Out1. Okay, so it kind of does this sequentially, and it really makes sense to have models that do this. So we just carry on until we get to our last one, HT, which represents kind of the final time point. And again, it would have the last input and it would have the last output. Okay, and you know, in machine learning, everything is done in matrices. So it would require a matrix, some kind of weighting matrix that takes it from I to H for the first time point, and then it would require another weighting matrix to produce the output from the hidden state. So it would go hidden state to output not, and then you'd have another. Maybe I should actually do this in another color to make it obvious. Let me get another color. Okay, so here's your W matrix from input to output not, W matrix hidden to output not. Oh, I think I said, so sorry about that, but my camera died for a second. But yeah, so I think I said this was input to output, but it's actually input to hidden. So we have another weighting that takes us from hidden, the last hidden, to the next hidden. So we'll have hidden to hidden not. Okay, so as you can see, each one of these requires an independent, sometimes, maybe sometimes not independent, but we can assume that it requires its own kind of weighting vector. Okay, and it happens kind of in this sequential way. Okay, where each value depends on the value before it. And it kind of happens like one at a time, okay? And there's some bottlenecks associated with this, which I'll get into shortly. So that's recurrent neural networks. Let me write it down. Recurrent, how do you spell it? Sorry guys, I'm really bad at spelling. That's your kind of recurrent neural network. I'm going to use NN to represent neural network. And then we have convolution that they mentioned. So what is convolution? Convolution. Okay, it's like this. So it's most kind of common in imaging, where you have kind of some kind of image and you have pixel values. So it's kind of in a grid where the location in space matters. So it encodes some kind of context based on its relationship to one another. And then you have some kernel, okay? So for example, let's say we have a 2x2 kernel. So there's 4 kind of pixels here. And it will convolve this image. So what that means is basically it slides across the image, and it performs an operation where each pixel value in the image is multiplied by each pixel value in the kernel, and then it's basically added up together, and it produces one single output. So this convolution will take the first, the second, the one below it, and then this one also. It'll multiply it by the weighting corresponding to each pixel, and then it'll sum them together. So you can think of it as like a weighted average of the pixels in the 4 little neighborhood. Now there's so many different things that you can do with pixels, convolution. One of them is, for example, edge detection. So let's say we have an image, and again, it's made out of these little pixels, and we have an edge right here, okay? So here's an edge, and this area is darker than this area. And then let's think about how the pixels behave as we go across the edge, okay? So let's say these are the pixel values. Well, then this pixel will have a value of, let's say, 0. And then again, this pixel value will have a value of 0 too. What value will this pixel have? Well, now it's on the edge. So it'll have a value of 1. This one will also have a value of 1. So let's say we have a kernel, just like two little squares kernel, okay? As it slides across the image, let's say we want to do a difference between the two values, right and left. So that would mean we'd have a weighting of, let's say, 1 and then -1 here. So each value we encounter, we will multiply it by 1 if it's the leftmost pixel, and then we'll multiply it by -1 if it's the rightmost pixel, and then we'll sum it up. So for example, if that kernel was placed here where there's no edge, and both of them are 0, okay, so we're in the light zone here, then it will have 0 times 1 minus 0 times 1, so it would be 0. Okay, so here it would produce a value of 0. Let's say this is output. It would be 0. If it's in the completely dark region here where we have 1 and 1, 1 times 1 minus 1 times 1. So again, that's 0. Okay, but let's say it's right on the edge where this value is equal to 0 in the image, and this value in the image is equal to 1. In this case, we would do 0 times 1, 0, and then 1 times -1, -1. 0 minus 1, it would be -1 here. So now, all along the edge, we would have -1, and everywhere else it would be 0 in the output of our convolution, okay? So now, when we kind of map it in some way, for example, we plot it as an image, we would kind of get a darker region here corresponding to the edge. So that's kind of one example, but there's so many different features you can extract by just convolving an image or any sequence data. So in this case, since we're talking about text, it's probably like this, some kind of vector, where each square represents a word. So let's say it's I love is this one, and then this square is cats. Okay, and when I say a square, I really mean a vector, because all of these words are embedded in some kind of vector space. Okay, so instead I'm representing it as one square, but you can think of it as having another dimension going this way. Okay, this way, this way, this way. And it has some kind of values in some higher dimensional space. I think they call it D model or something. I don't know, I'm sure we'll get to it. Okay, so that's kind of convolution. And then again, we have some kind of kernel, and we convolve it with it. So we think of it as taking a weighted average and then having one value, and then we slide that along. So then we do it here again, where it's one shifted over, and then that produces the next output. Okay, so does that make sense? Perfect. Okay, so let's continue reading here. Okay, so most of these transduction models, which again are sequence-to-sequence models, are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. Encoders and decoders are usually something that take in some kind of vector input and then embed it into some kind of, so let's say the input is X, and they embed it into some latent space, kind of Z, where this is some higher dimensional vector, and then this is also some higher dimensional vector, but they're not necessarily the same size. Usually this kind of dimension is smaller than this input dimension. So that's kind of encoder, and it maps some kind of input, in this case a word, because we're talking about like translation and next word generation, and then it outputs some kind of latent space, okay, some kind of embedding into some other space, where the values here associated with the vector in of the word in latent space are completely kind of esoteric, and they don't really mean the same things as this. And then we can process it, do something to it, and then we can kind of have the reverse at the end, and it's called a decoder. And what it does is it learns to take in this input latent space and process it and produce an output that's also in the same space as the input. So in this case, it would be back to a word, okay? And we're going to call that Y, which is the output. So again, we have a word here. Let's say it goes in a word, for example, cats, and it would do some processing, embed it into some latent space, some vector space in a different dimension, and then the decoder, encoder, see, I can't spell, will do the reverse operation and unembed it into the same space as our input. So in this case, it would be another word. Whether it's a word in a different language or the same language, that's the question. But this is kind of an encoder and decoder generally. Okay, so the best performing models also connect the encoder and decoder through an attention mechanism. Okay, so we're going to learn more about these attention mechanisms in this paper. There's a huge section on attention mechanisms. Hopefully I'm able to get to it in this part. If not, this might have to be split up into a multi-part series. I hope you're okay with that, but I prefer to kind of go slowly and really read everything carefully. We propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing the recurrence and convolutions entirely. Okay, so they're proposing now the transformer, which only has the attention mechanism, which was already previously described in recurrent neural networks and convolutional neural networks. But now it completely got rid of that recurrent and convolutional aspect of the neural networks. So they're basically making an argument that it's not really necessary, but the attention is necessary. Therefore, attention is all you need. Isn't that beautiful? Experiments on 2 machine translation tasks. Okay, so now we're seeing that this is actually a machine translation that they're implementing this on. Okay, so I know ChatGPT, modern day, when you chat with it, it takes in an input, which is kind of your sentence up into a certain point, and it predicts the next word in that sequence of words. But in this case, when it was first developed, it was not actually meant for that. It was meant for translation, okay? And that's what they're testing it on, machine translation. Okay, so experiments on 2 machine translation tasks show these models to be superior in quality while being more parallelizable, that's important, and requiring significantly less time to train. Okay, so faster and more parallelizable. Usually they go hand in hand, because if something is parallelizable, it's probably also faster to train. Our task achieves 28.4 blue. So blue is just some kind of metric that they use to assess how good the translation was. So it produces 28.4 blue on the WMT 2014 English to German translation tasks, improving over the existing best results, including ensembles. Ensemble learning is a technique that's used in machine learning where you train multiple different models on the same task, usually simpler models. Instead of having one really accurate, complex models, you would make a bunch of kind of smaller models. And you would make them perform the exact same task, and then in the end you would kind of average the result. And ensemble learning pretty much always leads to better results than just independent, okay? But they're saying this even outperforms ensemble learning. For over 2 blue, on the WMT 2014 English to French translation task. So you see when they say this WMT 2014, English to German, English to French, that's some kind of database that they used to train this model and to evaluate it. So what it probably is, it's some kind of data, something like this, where you have a bunch of sentences, okay? Let's say this column is kind of a bunch of sentences in English, and then this column is a bunch of sentences in either French or German, and it's labeled data where you know the English and you know the official kind of translation in French. So you would input that, but again, you would only input maybe a portion of it. So let's say this would be used for training, and then this would be used for testing, and test. This would be used for testing, and then you would evaluate on that. Okay. Okay. Our model establishes a new single model state-of-the-art blue score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training cost for the best model from literature. So, again, even though this is super fast, you can see how much time it takes. It takes 3.5 days to actually train it using 8 GPUs. I'm assuming these GPUs are expensive and big GPUs, and that probably run them a few thousand per GPU. So even with 8 GPUs that are probably really expensive to run, maybe even need some kind of cooling system, I don't know. But even with GPUs, and what is a GPU? It stands for Graphical Processing Unit, and it was first developed for video games, just to render graphics on video games, but then they discovered it's actually really efficient for matrix multiplication and any really parallel task where you have parts that can run in parallel, because it's kind of composed of these like threads, is what it's called. It's these little threads where you can send a task to one thread, but you can send little bits of tasks. So if you have a major task where you have maybe 1 million operations, you can split it up amongst the many threads in the GPU. As long as the result of one doesn't depend on the other, they can all run in parallel. And it speeds up matrix multiplication, which is the backbone of machine learning. So if you are interested in machine learning, I really encourage you to learn some things about linear algebra and matrices. Maybe we can get into that in the future. If you have an idea, comment down below, okay? Anyway, so it took 3.5 days on 8 GPUs, a small fraction of the training cost of the best model from literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. Did I say what constituency parsing means? Yeah, I did. So I wrote here, constituency parsing, analyzing a sentence to identify its hierarchical grammatical structure by breaking it down into constituents. Okay, so I'll read that sentence again. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. Okay, so we've basically now read the abstract, which gives us an overview. So now we know that most transduction models, they're trying to tackle this problem of transduction models being not very accurate, requiring a long time to train, being slow, and previously were implemented using recursion or recurrent neural networks or convolutional neural networks, okay, in the past. But now they're introducing this kind of more simple architecture, which is faster and, gets rid of this kind of extra stuff and only really has this this attention mechanism. Therefore, the name attention is all you need. And we see that it actually outperformed previous models. So yeah, that's basically the most important part of this paper. We can also see the authors here written, the author list, okay? It usually tells you where they work. So Google Brain, Google Research, University of Toronto, Google Brain. And usually the order in a paper matters because usually the first author is the one who contributed the most. However, you can see there's this little asterisk here, okay? And this little asterisk, we have to look here and figure out what that asterisk means, because it means there's some kind of note going on here. If we look down, it says equal contribution listing order is random. Jacob proposed replacing recursive neural networks with self-attention and started the effort to evaluate this data. So it gives you this entire synopsis here of more information about the authors, and it says that the author list is actually all equal contribution. So all of these people, oops, out of frame, all these people were actually equal contributors, okay? So now we have finished the very first part. Next, we're going to flip through the paper just to get a general feeling of what it is. So we have the introduction, which introduces the problem that they're trying to solve. So transduction or translation. Then it's going to give us background of other methods that have already been used to solve these kind of problems. So here we're going to be talking about recursive neural networks, convolutional neural networks. Then it's going to get into the methods. So here it's called model architecture, but usually in a general sense, when you're reading a paper, it's the methods of the paper, and it describes how or what they did and how they did it, what they did and how they did to solve the problem that they're tackling in the paper. And then we have here this beautiful little pictogram of the transformer as proposed in this paper. We have the encoder on this side, the decoder on this side, and I'm going to be explaining to you kind of the encoder and the decoder and take you through this, okay? But basically, you have your word input here. It goes through this attention mechanism, then a regular feed-forward network. Simultaneously, in the decoder, we also have input in the target language that we're trying to translate to. It also goes through this attention mechanism, and then both the words are fed in together. So now we have attention across the target language and the output, the input, which is the text we're trying to translate. And we do attention across them, and then we have another feed-forward network. And finally, we have our output, which includes the new token we are trying to predict. So, here they talk more about the encoder decoder. Then we get into this attention. So we have scaled dot product attention. We have multi-head attention. This is kind of the attention equation here. And then we have more attention information. And then we get here into the feed-forward network. So now we're done with attention. Now we just have kind of a regular sort of multi-layer perceptron. I have a little mark here. Then they get into other preliminary stuff, including embeddings. So the embedding is the part that takes in the word and puts it into some kind of embedding space. So some kind of space where it's a higher dimensional vector representing each word. So they talk about that. They also talk about, the softmax. Okay. This is what I wanted to get to, the positional encoding. So that tells the model, or it kind of tells the words, if based on the order where they are, it changes kind of their meaning so that the order is better represented between the words. Because again, the order of a word in a sentence does change the meaning. For example, if I say John is going to Anne's house, it's different than Anne is going to John's house, because the order matters, and we know that in English, the first person you say is the one who's doing the thing, so going to someone else's house, and we know the house is later used in the sentence because he's going to Anne's house, okay? So that's important to capture. And then we have why self-attention, okay? And then we're kind of done with methods here. You can see this is kind of where we break off from methods and we get into training, okay? Training. So this is kind of the least interesting part. the most interesting part is really the methods of the paper. Some more kind of, I don't know, training stuff. And then we have our results. Yeah, so obviously the results have already been spoiled in the abstract. But, you know, this is not a book. This is a research paper. So we don't need that much mystery. So yeah, we have some other things here. I don't know if we're going to get this far into the paper, unfortunately. But I really want to kind of capture the methods, which I think is the coolest really part of this paper, is how it works. And again, it's the building blocks of even your transformer model that we use today in ChatGPT. But the ChatGPT model doesn't really have the same encoder-decoder. It usually just has kind of this decoder architecture where you have a word, or you have a sentence up into a certain point. So for example, I love cats and is your input. It's processed through these attention mechanism, through some kind of feed-forward network, and then it outputs I love cats and the next token, which is maybe dogs, with high probability dogs. But it actually is not just dogs. It outputs a probability across all of the words in the dictionary that it could be. So maybe 95% that it's dogs is the next word. And then maybe 5% that the next word is hamsters. Okay? And then 1% that it's some other animal. Okay? But it's actually a probability distribution, which is why we do softmax. Softmax is really what gives us a probability distribution. Okay, so let's get into reading the introduction now. Okay, so it says, I'm going to start off by reading it, and then we're going to go through the notebook, and we are going to kind of elaborate some more on what we just read. Okay, so here I made some notes. So here we have kind of recurrent neural networks, convolutional neural networks. Okie dokie. So it says, recurrent neural networks, long short-term memory, and gated recurrent neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems, such as language modeling and machine translation. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures. Recurrent models typically factor computation along the symbol positions of the input and output sequences, aligning the positions to steps in computational time. They generate a sequence of hidden states, ht, as a function of the previous state, ht-1, and the input for position t. So again, that's what I already talked about. So each state, for example, this state depends on the previous state, which is also some kind of vector. That previous vector is fed into the current state. And it also depends on the input of that sequence. So let's say the first word was I. Well, this one is love. The next one is cats. So this state that produces this output at time point 2 only depends on the previous hidden state, the next word that is in the sequence, and then it produces an output. So that's kind of what it said here. Okay, this inherently sequential nature precludes parallelization. So that's important, okay? Precludes parallelization within training examples, which becomes critical at larger sequence lengths. Larger sequence lengths, as memory constraints limit batching across examples. So what's that saying? It preludes parallelization within training examples. So if we have a sequence of words that we're trying to translate, for example, I love cats. Well, you see, for example, love, well, we have to wait for the computation before it to finish before we can move on to the next computation, right? So we have to actually wait for this to finish before we can get to this one. And even in the third word, so I love cats and So we have our input and, but we also have the hidden state, which we have to wait for it to finish before we can go to the next one. So we can't really parallelize it, or we can calculate, let's say, each of the outputs at the same time. We can't do that because we actually have to wait for the one before it to finish before we can move on to the next one, because each hidden state from the previous step affects the next one. Okay, so that's an important point here. It's not really easy to parallelize, unfortunately. Another important thing that it mentioned was that and then also we have memory constraints. Okay, so it says memory constraints here limit batching across examples. So what does that mean? It means that you actually, so the way that these are trained, if you recall, hopefully you have a little bit of knowledge already, but we actually have back propagation, which means that first we do a forward pass through the sequence to derive all of the values in the output, and then we go backwards and update all the weights based on how different the output is from the true value. Okay, so again, we go forward and then we go back, and we actually have to store all of the values. And if we have a really long sequence length, for example, we have an entire book passage with like 1,000 different words, well, that means we have to store all of these hidden states and W vectors, weighting vectors. These weighting vectors are actually the learnable parameters in this case. We have to store all of that so we can later update it using backpropagation. So clearly the memory constraints become huge, especially with really long pieces of text. So these memory constraints limit batching across examples. Recent work has achieved significant improvements in computational efficiency through factorization tricks and conditional computation. So that's just kind of some tricks that they do to speed up the process. Conditional computation means that maybe sometimes we skip some computations, but it really doesn't make a huge impact. While also improving model performance in case of the latter. Okay, it improved model performance. The fundamental constraint of sequential computation, however, remains. So again, these recurrent neural networks are sequential by nature. So in order to calculate the next one, we have to wait for the last hidden state to have finished calculating. Which becomes kind of a problem because they're just naturally not parallelizable due to their sequential nature. But their sequential nature is also what makes them really good at these sequential tasks like language processing. Okay, next paragraph. Attention mechanisms have become an integral part of compelling sequence modeling and transduction problems in various tasks, allowing modeling of dependencies without regard to their distance in the input and output sequences. Okay, so attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing for modeling of dependencies without regard to their distance as input or output sequences. So now it's saying, actually, attention has already been implemented, and it's able to connect. What was the words that they used? Allow modeling of dependencies without their so it's able to connect words at very large distances. And if we think about it, for example, in recursion, well, in recurrent neural networks, if a word is at the beginning, it's probably not really affecting the word at the end, because each word only depends on the hidden state of the word before it. So each word can be highly dependent on the word before it, because it just happened and it just contributed to the value of the hidden state. But the first word might not actually affect it very much. And this is a problem, really. This is a huge problem, because in a lot of text, the things that come later, the things that come before a word in a sequence are what sets up the context for the words that come later. So this becomes a problem. And same with convolution. I show convolution here, kind of where we have like a bunch of words, and we have word 10 and we have word 30. Well, how are word 10 and word 30 going to interact? Well, you could have a really large kernel, which convolves them, but then look at what it's doing. It's finding a weighted average across 20 different words, because the length is 20. So in order to join the context between the 10th word and the 30th word, you need to have a huge kernel or a huge stride length. Or you can have a small kernel that doesn't average so many words, because when you have a long kernel like this, it averages all of these 30 words. So the context from all of these words is kind of being smeared together, and it's hard to really gain context. But, I shouldn't have deleted that because we actually need this. But if you have maybe a small kernel of like length 3 or something and slide it across and convolve it, well, in that case, it can kind of preserve more of the context, because now we're only averaging between the word before it, the current word, and the word after it. But then word 10 and 30 don't interact unless we have many, many layers of this small kernel. So we stack it up in many layers. So first we do one convolution with a small kernel, and then we take that as the input to the next convolution. We do it again, and then we keep doing this in many layers. And all of a sudden we have a bunch of complexity that we've added into the problem with all of these layers, okay? So, it's hard for, in convolution and in recurrent neural networks, it's extremely difficult for words far away in the sequence to actually interact, which is a huge problem, because we do want words to kind of talk to each other, even if they're far away. So, where were we? In all but a few cases, however, such attention mechanisms are used in conjunction with recurrent networks. So sometimes attention is actually used in recurrent neural networks. How does that work again? So what they're saying is that there have actually been recurrent neural networks that don't actually look like this. They don't actually look like this. Instead, they have this attention mechanism. And they have a completely different kind of, where's my paper? They have a completely different architecture where you have some kind of input, okay? And you have all your words, okay? So this represents all the words. I love cats. But actually, each one of these itself is a matrix, a vector, okay? So we have this vector. They're all the same dimensions. I just can't draw straight. But you kind of have this kind of sequential, you have this recurrent neural network first, where you feed each one into each hidden state, H0, H1, H2, whatever, forever, and it produces this output in some embedding dimension. Not 1, 2, 3, and then you actually have them talk to each other with their attention mechanism. So attention has been used previously, even in recurrent neural networks, and you allow them to transfer attention. So now you've actually created another, I'll call it Z primes. So these are our embeddings after they have kind of spread their attention towards each other. And then you kind of have this similar recursion where, recurrent network where you have some other hidden state. So now instead of calling it H, let's call it J, J0, and then you have your output not. And then you have your second hidden state, J1, and then you have your output 1, okay? So hopefully in this case, I love cats, let's say you're translating it, it would be j'aime, these would be your outputs, j'aime les chats, okay? And then this would happen with all of these hidden states. So attention has been previously implemented. So in a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. In this work, we propose the transformer. A model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state of the art in translation quality. after being trained for as little as 12 hours on 8 P100 GPUs. So I can actually Google how expensive those are, but I can't right now because I'm filming a video. Okay, so let's move on now to reading the background. The goal of reducing sequential computation also forms the foundation of the extended neural GPU, the ByteNet, and the conv S2S, all of which use convolutional neural networks as building blocks, computing hidden representations in parallel for all input and output positions. So now they're kind of reviewing the literature, and they're letting us know that this actually problem of reducing the sequential computation common in recurrent neural networks has been targeted already with convolutional neural networks, because in a way they are more parallelizable because they don't really occur in a different sequence. So if we go back to this kind of picture where I drew our convolutional neural network, well, we know the kernel values are kind of consistent, and we know the input image. So within a layer, we can calculate all of these kernel outputs individually at the same time in parallel by sending each convolution with each position to a different thread in the GPU. So for example, thread 0 in the GPU would receive a computation of the first 4 pixels here and the convolution with the kernel. And then we would slide the kernel over, but it would actually happen in parallel, but this is kind of the next computation, is we would slide the kernel over, and then we would do it again for this. So this part, this computation, would be sent to the next job in the thread in the GPU. Okay. So they are more parallelizable. All of these use convolutional neural networks as building blocks, computing hidden representations in parallel for all input and output positions. In these models, the number of operations required to relate signals from 2 arbitrary input and output positions grows with the distance between positions. So that's important, and that's something I talked about. The number of operations required, so that means how many times do you have to convolve with a kernel across the sequence. The number of operations required to relate signals from 2 arbitrary input or output positions grows in the distance between positions. Linearly for conv S2S and logarithmically for ByteNet. Now these are previously introduced models and architecture, which I'm not really going to do a deep dive into. But I'm sure you can Google these if you are really curious and you want to find out more. This makes it more difficult to learn dependencies between distant positions. In the transformer, this is reduced to a constant number of operations, albeit at the cost of reduced efficient resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. So let's read that again because that's so important. In the transformer, this is reduced to a constant number of operations. So that means no matter how distant the words are, they all kind of have an equal chance of affecting it, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. So we're kind of going to get more into this, and to be honest, now that I'm reading it, I don't really understand what that last sentence means. But self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute the representation of the sequence. So we have some kind of sequence, okay? And let me draw this. So basically, you can think of attention as, if I have a sequence of words, I love cats. So then they all have some kind of meaning. I has an independent meaning, love has an independent meaning, and cats has an independent meaning. But since they're strung together in the sequence, they actually affect each other, okay? So because love and cats is paired in this way, maybe the cat becomes a little bit more lovable, okay? A good example of this is, let's say, the word bank. So let's say I have two different sequences. The river bank. And I have another, which is the ATM bank. I don't know if ATM is a word, but let's say it is. In this case, we have the word bank in both of these. But do they have the same meaning? No. In the first one, we're actually talking about a riverbank, a body of water, okay? The second one, we're talking about a physical bank where you go to input money into, okay? So these are very different things, but they're technically the same word. So when we first do the word embedding process, we embed the word bank as some kind of vector, okay? Like this. And we think of it as a vector because it's really composed of a bunch of different kind of positions in space, you know? I mean, maybe it has like X, Y, Z coordinates. Left hand principle, left hand rule. Right hand rule. Dyslexic, guys. So we have this kind of embedding vector for bank. But once we allow the words around it to influence each other through the attention mechanisms, well, then the embedding and the meaning of the word bank actually changes. So in this one, the word bank is associated now, let's say it shifts into the water dimension. Okay, sorry. So my camera died, but I don't know how much of that you missed, but I kind of explained how in the sentences, the river bank and the ATM bank, even though the word bank is used in both cases, it takes on a different meaning. So in the river bank, it corresponds to water, and in the ATM bank, it corresponds to a place where you go to deposit or withdraw cash or money, a place that like holds your money for you. So when we have the vector embedded for the word bank, it's embedded into some kind of vector space where each dimension represents a meaning, okay? So in this case, it's embedded into some vector space. This is the initial kind of starting point, and then the words around it influence, the context influences the meaning of the word bank. So, for example, river might shift bank and translate it more into maybe the water direction or the forest direction. So it ends up being a different vector versus bank 2, which is maybe translated in a money or financial direction. And at the end, even though initially we started off with this is my XYZ axis, we started off with bank being this, well, afterwards it kind of branches off into two different banks. So we might have it pointing this way, and then we might have the other one pointing this way. So now they point in different spaces. So this is bank 1 referring to an actual river bank, and then this one is bank 2 referring to a place where you go to deposit money. So where were we? What did I read so far? So multi-handed, okay. Self-attention, sometimes called intra-attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in a variety of tasks, including reading comprehension, abstractive summarization, contextual entailment, and learning task independent sentence representations. So here they list all the tasks where this kind of attention mechanism has excelled, okay? So, self-attention has been used successfully in tasks that involve reading, abstractive summarization, contextual entailment, learning tasks, independent sentence representations. So it's mostly just language, kind of language processing tasks. That's kind of the common theme here. So then it says, end-to-end memory networks are based on a recurrent attention mechanism instead of sequence-aligned recurrence, and have been shown to perform well on simple language question answering and language modeling tasks. So in kind of summary, to summarize this, these kind of things are good for text-based problems. Summarization, predicting the next token, stuff like that. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its inputs and outputs without using sequence-aligned recursive neural networks or convolution. In the following sections, we will describe the transformer, motivate self-attention, and discuss its advantages over models such as, and then it kind of lists all these models. So this is kind of important. The transformer is the first transduction model relying entirely on self-attention to compute representations of inputs and outputs without using sequence-aligned recursive neural networks and convolution. This is kind of our thesis sentence that summarizes transformers. It doesn't use recursive neural networks or convolution. It's a transduction model, and it relies entirely on self-attention. So now let's hop into the model architecture, which is kind of the methods section. The method section, okay? Most competitive neural sequence transduction models have an encoder and decoder structure. So that's here. This part right here is our encoder. Oh, I'm out of frame. And then this part here is our decoder. Okay. So they say most have this encoder and decoder structure. Here, the encoder maps an input sequence of simple representations x to xn, so that's kind of our input sequence, and then it maps it to a continuous representation of sets. Okay, so that means the input here is our language that we want to translate. So over here we have x1, x2, all the way to xn. Okay, this is our input, and then it goes through this kind of attention mechanism in our encoder, and our output is some kind of embedding space. So it does some kind of transformation to it, and I mean some kind of transformation. What I mean is it applies this attention mechanism, and it applies a feed-forward kind of normal, regular old neural network, and then you have some kind of latent space embedding, and then that is being fed. So that's the output and from the encoder, and it's being fed as input into the decoder. And then it says, given Z, the decoder then generates an output sequence, Y1 all the way to YM. So notice there's an M here, so it's not necessarily the same length as the input sequence. So again, it takes in this input, and over here it's actually whatever it figured out so far in the sequence, okay, from the previous step. But we're going to name it here. This is our output, y1, y2, all the way to ym. Okay, so this is our output. So for this, for example, could be the sentence we desire to translate. So something like, I love cats. I spelled it wrong. I love cats, okay? And then it goes through this, it puts it into some latent space, and it feeds it in, and over here it'll translate it into I love dogs, okay? But actually it does it one step at a time, okay? But let's continue reading. Okay, so at each step, this is important. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. So again, at each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall structure using stacked self-attention and pointwise fully connected layers for both the encoder and decoder, shown in the left and right halves of figure 1. So over here you can see that the input is the output shifted to the left. So it's whatever came out of this previous one but shifted so that there's an extra space, okay? So let's say last time it translated j'aime les, and then that's it. And then the next time it would have output, but it would be able to find the next word. So it'd be j'aime les chats. Okay, so then this would be the new output. Let's take a step back and read through some of my notes now. Okay, so again, we talked about recurrent neural networks. They're inherently sequential, and which limits the ability to parallelize. For longer sequence lengths, there's memory constraints. That's kind of the pitfalls. And also, yeah, so for long context windows, there's memory constraints. Attention mechanisms are also a part of sequence modeling and transduction, allowing models of dependencies without regard to their distance in the input and output sequences. So when we have attention implemented, it's actually able to connect words that are very distant within a sequence. So that's kind of a pro of attention. And we'll kind of get into the matrices of how they do that. In an attempt to reduce sequential operations, convolutional neural networks are used to compute hidden representations in parallel input and output. So, to mitigate this problem introduced by recursive neural networks, convolutional neural networks were implemented. Okay? The number of computation operations required to relate signals from two arbitrary input or output positions grows with the distance between the positions. So there's still kind of the problem, even though convolutional neural networks can be parallelized. This line at the end is pretty important. So it says, at each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. Now, I don't actually know if it kind of does that. So here it's I love cats, and then it would produce one word at a time. Because, I'm just going to put on my chopstick. Because actually the masked multi-head attention should kind of cover that. So I don't really know about that one. Okay, then it says, the transformer shows the overall architecture using stacked self-attention and pointwise fully connected layers for both the encoder and decoder, shown in the left and right halves of figure 1 and 2 respectively. So encoder, decoder. And now we're going to talk more about the encoder and decoder. So in the encoder, it says, the encoder is composed of a stack of n is equal to 6 identical layers. Each layer has 2 sublayers. The first is a multi-head. Okay, so what does that mean, 6? So it has a stack of 6 identical layers. Each layer has 2 sublayers. The first is a multi-head self-attention mechanism. The second is a simple pointwise fully connected feed-forward network. That's this. So that means that each one, so this block kind of NX, so it incorporates the self-attention layer here and the feed-forward layer here. So this entire kind of box is 6 times stacked on top of each other. So really it's this box, and then the output leads to another exactly like this, but this time capturing another kind of attention of a deeper embedding, and then that would produce an output. So it actually looks like this, the encoder. So we have our words, okay? Words. Again, it's in the form of some vector. And then this dimension would be also like the vector. So this would be like I love cats, where this represents I, this represents love, this represents cats, this represents and, this represents dog. And then this would be the dimensionality that we're embedding the words into. So in this case, it would be 1, 2, 3, 4, 5, 6. 6-dimensional embedding space for the word I and for the word love and for the word cat. So each one of those is embedded. And then we'd have some kind of attention layer where we would allow these to speak to each other. So usually they do this in the form of a matrix. Okay, where this is I, this is love, this is cats, this is and, this is dogs. And then you'd calculate the attention between every word as well. I'll demonstrate that more. But this, and then it goes into a feed-forward network, which is kind of just a regular neural network. Let's say it's fully connected. So each neuron leads to each other neuron. Okay, and then it would go into another attention layer. So I'm kind of running out of space, but I don't know why I started this way. But let's say it leads to another attention layer here. So you'd have another attention, and then you'd have another fully connected, what do they call it? Feed-forward network or layer. And it would kind of do this 6 times, okay? So even though it's shown here as a simple attention mechanism and then feed-forward, it's actually a much longer kind of thing that's really compressed, okay? And the reason why is because each time you take the output and you feed it into the next attention layer, the attention works on a different embedding of the word, because attention lets the words speak to each other, and then the feed-forward layer embeds the input into a different space. So that means that the vector that comes out of the feed-forward network, now the dimensionality might be different, or it might be the same number technically, but the dimensions and like what the dimensions mean in each direction changes. So it kind of captures different parts of the word. And that's really what embeds the meaning, okay? I don't know if that makes sense, but we'll continue reading. Okay, so again, there's 6 layers. Each layer has 2 sublayers. The first is a multi-head self-attention mechanism, and the second is a simple position-wise, fully connected feed-forward network. We employ a residual connection around each of the 2 sublayers, followed by layer normalization. So this residual connection is here, so that means the values here get fed into the output, and they're added into the output, even if, so you can see kind of this one here. Maybe I should erase this because it's getting kind of messy. But the value here, you see how it has this arrow that connects it, and it says add and normalize. So that is taking whatever the input is. After we apply the attention, we're actually still adding the initial value, okay? And then we kind of do that with the feed forward as well. So even if the weightings determine some of the inputs are maybe set to 0 or inactive, it's still being added to whatever the initial value was, okay? So that's kind of what these residual connections are. And the reason why they're implemented is to prevent gradients going to 0 when you have kind of many different layers. Sometimes as you back propagate, because when you back propagate, you're using the chain rule, so you have a bunch of partial derivatives, so the derivative of loss with respect to like the first one multiplied by it's just kind of you do the chain rule all around. Sometimes the values are small, less than 1, and when you multiply a bunch of values less than 1, the derivative ends up being 0 and the gradient vanishes. And if the gradient vanishes, then we don't really know how to change the weights, okay? So a way to mitigate that is using these kind of feed-forward residual connections. So it says, we employ residual connection around each of the two sublayers, followed by layer normalization. That is, the output of each sublayer is layer normal x plus sublayer x. Okay, so that means that, let's say this is our sublayer. So we have attention and then feed forward. X is the input into the sublayer. Okay, so this is our, let's say it's like sublayer 4. Okay, so then x is our input into this attention, and it's again a vector. So we have x0, x1, x2, all the way to however long the x is. And then here, the output, well, we have whatever the function is. So let's say this entire thing can be viewed as f at x. But since we have this residual connection here, the output here is actually x plus f at x. And then it's normalized. Okay. So that's really what this is saying. Where sublayer is the function implemented by the sublayer itself. So that's the attention mechanism and the feed-forward network, which is applied at every sublayer. And again, this is stacked 6 times on top of each other. To facilitate these residual connections, all sublayers in the model, as well as the embedding layers, produce outputs of dimension d model is equal to 520. So this is the dimensions. This is how large the dimensions are, 520 different spatial dimensions. So that's pretty high dimension. Think of this, we can only move in 3 dimensions, okay? So we have all of these words kind of are embedded in 512 different dimensions. Now let's move on to the decoder, which is this part of the network. So the decoder is composed of a stack of n equals 6 identical layers. So that means that we have, again, this layer shown here by nx is stacked 6 times. So the output of this goes into a new one exactly like this, okay? 6 times. In addition to the 2 sublayers in each encoder layer, the decoder, okay, in addition to the 2 sublayers in each encoder layer, so the 2 sublayers, I think, are this, 2 sublayers, and the decoder inserts a 3rd sublayer, which performs multi-head attention. Okay. So it says, in addition to the 2 sublayers in each encoder layer, the decoder inserts a 3rd sublayer, which performs multi-head attention over the outputs of the encoder stack. So that's this one. This is kind of the new layer in the encoder. It takes the output of the encoder, which has provided context into I love cats. So now I love cats is in some latent space represented by Z, where the attention mechanism has been applied. So the words I love cat now have contextual meanings. And we also have this feed-forward network, and this is stacked 6 times. So by the time the output leaves the encoder, it should be a pretty accurate representation in latent space of what actually each word means with its context, with its order in the sentence. And that's fed into this, okay? Into this part, the multi-head attention of the encoder, okay? And then here, the attention is actually measured comparing the already translated part with the embedding of I love cats. But this is also kind of, transformed through attention. So first, j'aime les, so that's the translated part. This part is fed through this attention layer, so the words get to speak to each other, okay? And then here we compare I love cats with j'aime les blank, okay? So now we let these two share context, and that creates just one kind of embedding here. And let's call it J naught, J1, all the way to Jn, okay? So now we have some kind of embedding here, which combines both of these, the part of the sentence that has already been translated into the target language, and the input, which is the desired kind of translation in the original language. So now they're able to talk, and we go through this kind of feed-forward network. And again, this is performed 6 times, I believe. Similar to the encoder, we employ residual connections at each sublayer, followed by layer normalization. We also modify the self-attention sublayer. So self-attention sublayer, I think that this is the self-attention sublayer, so that's the one before this one. So this attention sublayer, look at the inputs. It's the output from the encoder and the output from the last attention from the decoder. So that's not self-attention, because it's calculating the attention between the target the translation that we input into the model, and then the part that's already been translated into our desired language. But this part is just self-attention. So here, when we're measuring attention, we're calculating the attention between j'aime les and j'aime les. So it's actually all the words get to talk to each other. So here, for this part, you can think of it as all the French words get to talk to each other and influence their meanings and embeddings. J'aime les. So now these get to talk to each other. So maybe these are influenced like this. And then here, at this attention mechanism, well, here we let j'aime les and I love cats talk to each other, okay? So now they get to chit-chat together, and that's when a value is kind of outputted from here. So this is how the model kind of knows what it's supposed to translate next. Okay, so then which performs multi-head attention? Okay, so where were we? In addition to the 2 sublayers in each encoder layer, the decoder inserts a 3rd sublayer, which performs multi-head attention over the input of the encoder stack. Okay, so that's the input of the encoder stack. That's this. Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. Okay, so that means this one is masked. So that's important. So the masked attention means that we only let words before each word affect the current word. So j'aime can be affected by je. Les can be affected by je and m because they come before it. But for example, m cannot be affected by les, and je cannot be affected by m or les, okay? So that's kind of this masked attention, and that's kind of the mechanism of how we make it autoregressive. So now if you have a complete sentence, we know the true value, but at each step it's also predicting the current value. So it's trying to predict m, and at the same time it already knows m when it's trying to predict les. So in each kind of step, to make training easier, it's trying to predict each word at each step, because it only lets it see the words before it and not after it, kind of to prevent cheating, is kind of a way that they say it. But yeah, I mean, it's just the way that it works. I mean, it can't know what the true value is of the word until it's done. Okay, so Similar to the encoder, we employ residual connections around each of the sublayers, followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. So that means all the values before it can affect all the values after. So all the words before can affect the meaning of all the words after, but the words after can't affect the meaning of the words before. So let's take a break there, okay, before we get into attention, and let's reference the handy dandy notebook I've created here, because I need some notes here, okay? So, competitive transductions models usually use encoders and decoders. Perfect. The encoder maps the input sequence of symbol representations to the sequence to another sequence of representations. So the input is shown as X. The encoder maps it to some embedding space. Then that gets sent to the decoder here. The decoder maps this to some other output space, which is the words that it's predicting. It's the output. And then it kind of has this autoregressive nature where at each step the model consumes the previously generated symbols before generating the next. And this is actually implemented using the masked attention mechanism, which we'll kind of get into. Okay, so this is kind of, in theory, how the model works, but really it's doing all of these at once. So let me bring your attention here. We have the model, okay? So the first time we input, for example, learning, but this example is more of how ChatGPT works, and it's not really how the translation tasks works, because in the translation task it would be translating it to a different language, but here we're just predicting the next word. But it's actually really similar. So if I were to make a similar thing, if I were to make a similar diagram for the model, okay, so let's say we have, this is our model. Okay. And then we have our first input. Maybe I'll take a different, I don't know if this one's gonna work better. Okay, so let's say our input is I love cats. I love cats and dogs, okay? So that's our first input. And then our output is going to be the target language. So this is our encoder input. Encoder. And this one is going to be our decoder input. So it's going to be just like, let's say, a new line representing that we have to come up with a word next. So this is like a new line character representing that there's a new word starting. So really, even this encoder will have a new line character, and it'll have an end line character here representing that the line is actually finished. So this is going to be the input to our decoder. Okay, so together that gets put in, and then the output is, maybe I'll do it with this black pen. The output is going to be from the decoder, okay? So then decoder gives the output all the time. This is true for all of the outputs here. And it's going to be the new line character, and then maybe it's going to be 2. Let's say it gets it wrong, okay? So 2 means you in French, but we're actually trying to translate I. Well, we know that the first value is actually supposed to be j'aime les chats. Et chien. So this is kind of our result. So we know that this is wrong, okay? But this is the right answer, so we're actually going to send the right answer in next time, okay? So the second time we send Again, we send the same encoder, but this time the decoder changes and everything gets shifted, as they say. So now the decoder is going to be the new line character, and then it's going to be this je, and then something blank, okay? And then it's trying to predict what the next one is. So this gets fed into the model, and it'll produce, again, the new line character, the je, and then it'll produce, let's say M. Let's say it gets it right. Okay, so that's right, perfect. So now this gets fed back into the model, and this time it'll be the new line character and gem, and then nothing. And that gets fed into the model, and then it's gonna predict what the next word is. And let's say it also gets it right, le. So this is kind of what it's doing. It has the input here embedded. The input here is the source text that you're looking to translate. It gets fed into the model along with whatever we have so far in the decoder. If we have nothing so far, we feed in this kind of start of the sentence character that tells the model we're just starting a new sentence, so come up with the first word. It goes through the model and it's always trying to predict the next one. How does it do that? Well, first it lets these guys talk to each other, and it also lets these guys talk to each other independently, so that each word changes the other word's context within itself. In the encoder and then in the decoder, all the words get to talk to each other to shift their embeddings. And then we have the cross attention, where we let these two speak to each other. And then finally we produce an output word. In the case of kind of ChatGPT or regular large language models, we don't really have two things that we're looking to translate. In that case, we actually have some kind of text. So learning, and we know the next line. So it's actually learning about machine learning. I know it's kind of silly, but the input text is, let's say, learning about machine learning, and then it outputs. So first we input learning. It guesses that the next word is. Unfortunately, it was wrong. So the next time we put in learning about, and then it'll, oh, this is not supposed to be machine. Oh, this is just supposed to be blank. And then the next time, it'll predict what the next word is. So in this case, it predicted learning about subjects. No, subjects was wrong. The true value we were going for was learning about machine. So then we put in learning about machine into the model, and then it guesses learning about machine code. No, the correct answer was learning. So this model is not very good yet, okay? It's still being trained. That's why it's making so many mistakes, okay? And then the next time we put in learning about machine learning is, so it kind of does it kind of this repetitive way, okay? When predicting the sentence, one word at a time is generated, and that new word is added to the end. So actually, even though I'm showing it this way, this isn't actually what happens. What actually happens is shown here. So this is with kind of the masked attention. So really, the entire sentence is fed into the model. Learning about machine learning is fun. That's the entire sentence. And then within one step, it's actually predicting all of the words, but we're masking. So for the first step, all it sees is learning. We're masking all the rest. It only sees learning, and then it's trying to predict the next word. For the second word, it allows it to see learning about. That's all it gets to see, and then it predicts the next word. So it guessed subjects. For the third word, it's allowed to see learning about machine, and then everything else after is covered. It's masked away from the model, and then it predicts that word. So this way, instead of having to iterate through the model many times, where we just put in one word, we're predicting one word at a time, which could take a lot of time. In this case, with using this masked attention, we put in one long piece of text, and one training example actually acts as many different training examples because it actually guesses every single word in the sequence by covering up all the words after it and only allowing it to see the words before it. Now, let's talk about the encoder. So, let me get my pencil. So the encoder, it says, it's composed of a stack of n is equal to 6 identical layers, which we discussed, aka a bunch of attention and feed-forward networks. And so these are the two kind of sublayers. It mentions that the encoder has two sublayers. Let's look at it and I'll go through it. So here is the encoder from the paper. So the first one is the multi-head self-attention mechanism. That's this one. The reason why it's self-attention is the words talk to each other from your input. So, for example, our input is I love dogs. That's our input into the encoder. All the words get to influence each other. So the word cats is influenced by the word love. It's also influenced by the word dog because this one is not masked, right? Only this one is masked. This one doesn't say masked. So actually, for this one, for this case, later words are actually able to influence previous words, okay? So we let all the words talk to each other, and then we kind of have this richer context with the words. And then the second thing we have is a fully connected feed-forward network. And here's kind of like a picture of what I drew. So this is the input to the feed-forward network, which is the words after they've gone through attention. And then they're fully connected, and then the output is some kind of latent space embedding. The residual connection is employed, okay? A residual connection, so that's what we talked about here, this residual connection. Around each sublayer. All sublayer inputs and outputs are this dimensional space, 512 different spatial dimensions where the word can be represented. Residual connection. The input to each sublayer is added with the output of that layer, then normalized. So that's kind of just the definition. Okay. And then the input to each sublayer can be modeled using this equation, which we talked about. So it's basically the input, x, plus whatever operation is performed on them during the sublayer, added together because we have that residual connection, and then we perform this layer normalization. Where sublayer is each sublayer's function, either attention mechanism or the FFN, but it's actually both of them. I don't know why I wrote this. So the sublayer is actually all the things that happen within a sublayer. So for the encoder, the things that happen within a sublayer, and again, the sublayer is just this part, it's the self-attention mechanism, and then it's the feed-forward network. For the decoder, this sublayer actually has an extra one here, an extra component, which is the multi-head cross attention between the words coming from the encoder, which are the thing you want to translate, and the thing that you already have in your target language translated so far. And we let them talk to each other so it can determine what the next word is. Okay. So now we move on to the decoder. And I will include, hopefully, I can put them both side by side so we can read about the decoder while also taking a look at the decoder. Maybe I'll do this. This is good. So this is your decoder, and then let's read what I wrote about the decoder. So the decoder is composed of a stack of n is equal to 6 identical layers, same as the encoder. In this case, it includes 3 sublayers instead of 2. The first is the masked multi-head self-attention layer. So this is the masked multi-head self-attention layer. So it's masked so that we prevent words leading into the decoder, later words to influence the meaning of past words. So this is what kind of gives us that speed up during training so that we don't have to actually put in the same sentence multiple times. We can put in a long sentence once and it predicts all the words, the probability of all the words. Okay. This presents positions from attending to subsequent positions, aka each position can only attend to position before it in the sentence. So I drew this kind of picture here. I love cats. We say cats attends to I and love. Okay, so basically in this I love cats, the word cats can be attended, or we say attends to, but the word for the word love affects the meaning of cats. The word I affects the meaning of cats, and they're allowed to because they come before it. But for example, love, the word I can affect the meaning of love, but the word cats can't because it comes later on in the sentence. So we don't let these two words interact. Okay, so this is kind of my chain of thought here. I might have word vomited a little bit onto this page. Words after the current word should not affect its meaning, since during training it's technically not known yet. Okay, so that makes sense. Technically the words after each word have not yet been generated, so they shouldn't affect the meaning of the words before it. However, I was thinking about it, and there are some exceptions to this. For example, what about the sentence, I went to the bank and deposited money for. The word bank is not being influenced by deposited or money. So in this case, when it's predicting the word bank, or if it's predicting the word bank, it won't know about deposited and money, okay? But if it sees this part of the sentence and it's trying to predict the word money, that means everything money and after is being masked away, and it can see I went to the bank and deposited. So now they're allowed to talk to each other, but everything else is masked, okay? So this whole masking thing, it's not rocket science. It just basically means that for the first case, it's only seeing the word I. Then it's only seeing this part. Then it's only seeing this part. Then it's only seeing this part. And in each case, only the words here before it can affect each word, okay? But for example, this is kind of the problem that I found out with it, is let's say it's trying to predict the next word after deposited. Well, even though we see the word deposited, technically bank is still not affected by deposited because it still comes after it in the chain. So even though we should technically let all of these words interact with each other, it's only trained in a way so that the words before it ever can influence it for this specific attention block. And we can't change that. Even if we're no longer in the training process, we're not allowed to change that, and we're not allowed to next time change it so that later words are able to affect previous words. So I kind of wrote that down here, and I'm going to read it out loud for you because I'm not sure if my explanation made that much sense, but I'm hoping once you read this, it'll make more sense. The word bank is not being influenced by deposited and money, okay? So in this case, only previous words affected, so only I went to the affect the word bank. But words like deposited and money, which give it a lot of contextual meaning, do not affect the word bank for this attention block because it's masked, even though these words are already generated. Okay, so even when we're trying to predict the word money, so we've masked out this section of it, even though technically the word deposited is already generated, it still does not affect the word bank because the word bank comes before it in the sentence. And this training block, this attention mechanism, was only trained such that only words before it can affect words, a certain word. So for a certain word, only words before it. But since the masked attention matrices are trained with masked attention, they cannot be changed after training to be non-masked. Okay, I'm hoping that made sense. Now, going through the decoder architecture, again, we have the input from the embedding. We have we have the embedded word part of the sentence that's already in the target language, the desired target language. We take it through this masked. No, this should not be masked. Oh yeah, sorry. This one is masked. So here we have the word, like the part of the sentence, like j'aime les chiens. So it's already in French. It's already the part that's generated. We have the masked attention, so that we let all the words influence each other's meanings within the sentence to get a richer embedding of the sentence in the target language. And then we let the cross attention go here. So over here, see, it's not masked. So in this case, later words can affect previous words. The reason why is because, in language, the order is not so consistent. In some languages, the order of the words would be completely different. So just because, I guess in French and English, it kind of matches up. The word je is the word I, the word aime is the word love, the word les is the word the, which isn't omitted here, right? But actually, in some languages, you might have to translate I love cats into cats love I, and it would be a completely different order. So in this case, we do not put masked attention because we want all the words to interact with all the other words. And then finally, we have this feed-forward network at the end. Okay, so we have the masked multi-head attention. All token words can only be attended to from words before it. I've already talked about this so much, I'm starting to bore myself. And then we have the multi-head attention, unmasked attention between encoder and decoder. Decoder words to be generated in the target language. Ask questions to the encoder words, source language to be translated. So this is kind of an interesting way that I've decided to think about attention. Is words are asking a question, and then all the other words are answering that question. How do words ask the question? It's through embedding it in a question query in key space. So we'll get into that when we talk about attention, but I just want to drive this point home here, is that to think of attention, I think a useful way to think about it is to think of attention as words ask questions and the other words answer that question. So for example, okay, maybe I love cats is not a good example. For example, I went to the bank and deposited money. So let's say we're embedding that, and the word bank, or the word deposited, for example. Let's say the word positive. It can be influenced by all the words before it. So the word deposited asks a question. It says, am I related to money? And the word and will respond no, because the word and doesn't tell us anything about money. The word bank would respond, yeah, we are money, yeah. It would say yes. The word the will respond no. The word to will respond no. The word went will respond no. And the word I will respond no. So now the word deposited, even though originally it means just to deposit something, to put something in something, well now it's changed its context, so it's actually deposited something money-wise. So this results in a translation in the money direction. Now it can ask some other questions. For example, am I associated with a destination or like a building or something, a physical place? The word and will say no. The word bank would say, yeah, a bank is like a building, yeah. The word the will respond no. The word to will respond no. The word went might respond yes. Well, you go somewhere, so yeah, you're probably a physical place, like a building or something. So now the word deposited is in a financial money setting, a context from the word bank, but it's also a physical context. So we're depositing money in something physical. We went somewhere, right? So that's how these words change their meaning based on the words around them. So each word asks a question. The words around it answer that question. If they answer yes, the word's value is changed. Okay? Okay. So now we're going to get into attention. So this is kind of the bread and butter of this paper. And let's read through attention. And I think we are going to stop after attention. So this is going to be kind of towards the end of the paper. And then maybe I'll make a part 2 with the rest of it. Okay. So this is kind of the most fun part of the paper. An attention function can be described as mapping a query and a set of key value pairs to an output, where the query keys, values, and outputs are all vectors. Okay, so basically we have query, key, and values. Query is a question. The key is an answer, and the value is if this question was answered yes to by this query, by this key, then how would the word change? So for example, if the word, if the word deposited asked a question, am I related to money? And the word bank responded, yeah, how would the word deposited change? Well, it would move in a financial direction, in a money direction. Okay, so the output is computed as a weighted sum, of the values, where the weight assigned to each value is computed by a compatibility function of the query and the corresponding key. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function for the query and the corresponding key. Okay, let's see what I wrote here about attention. And then maybe we'll go back to this part, the scaled dot product attention. We'll go on to this part next. But let's review what we just talked about. So in attention, we have a set of queries and key value pairs used to map the tokens, which are the words, to an output, or the output being a query key space. So first we were in embedding space, where we embed the meaning of the words, and then we apply some kind of matrix operation to the word embeddings to take it into a different space, which is asking a question and answering a question. And recall that, notice that they come in pairs. So we don't just have a question, we also have a key transformation, which is in the form of a matrix that accompanies the query. So we have some kind of weighting that changes the value of the embeddings, and then we have some kind of key matrix as well that answers the exact question within its pair. The queries ask questions which are answered by the keys, leading to a weighted sum of the values outputted. So again, the queries ask questions which are answered by the keys, leading to a weighted sum of values outputted. So what that looks like, here is D model. So these are all, this direction is D model, so that means each one of these squares is a word. So let's say this one's I, this one's love, this one's cats, this one and, this one's dogs, okay? So each one of these rectangles represents a word, and it has some higher dimensional space, specifically 512, which was mentioned in the paper. So that means we have 512 of these dimensions, and each one has a value which represents the word embedding. And then this is just the context window. So in this case, our context window is 1, 2, 3, 4, 5, because we're only taking 5 words. And then the query key and value matrices are applied to the words, mapping them to the query key space of dimension dk. So now dk is actually a lower dimension than the input. So these were in 512 dimensions. We apply some kind of matrix to this to transform each of these words into another dimensional space, which is a smaller dimensional space, except the value, which has its own dimension, size TV. Now, what dimensions these are is kind of arbitrary. I mean, you kind of choose a value and you stick with it. Will it make that big of a difference? Well, generally, if you have a higher dimensional space, you can embed more literally independent parts. So maybe you can embed more things about the word. So whether the word is associated with music, whether the word is associated with money, whether the word is associated with a positive or negative emotion. So that's kind of things that you can embed when you have more value, when you have more dimensions. But does it make a difference if you had 500 versus 600? Maybe not that much. It would maybe also make a computational difference in the sense that if you have higher dimensional embedding or word embedding, well, then your computation is going to take longer because you have to do a calculation over more values. So, of course, it's going to take longer. Okay, so now we're going to get into this equation, which we have to read the next part to discover. So it says, we call our particular attention scaled dot product attention. The input consists of queries and keys of dimensions dk. So notice dk is different than dm, which is the dimension, embedding dimension of the words, just regularly embedded. But now we have the key query space, which transforms the words from the embedding space into some kind of question and answer space. And now the dimension is dk. And values of dv. So dv is the value of the transformation. So this is again just a lower dimensional space, probably for computational efficiency. We compute the dot products of the queries and all keys. Divide each by square root of dk and apply a softmax function to obtain the weights on the values. So notice this. So Q represents the words embedded in query space after we've already performed a transformation, a matrix transformation to get it into query space. The K here represents the words embedded in a key space. And then we calculate the dot product between them. So CQ is a matrix, K transpose is a matrix. When we transpose it, we take the dot product. So it's basically we multiply all the values and sum them together along its dimensions. And what is the dot product? The dot product, if you have two vectors, the dot product is asking how much of one vector overlaps with the other vector. So, I'm out of frame. So for example, if this was our key and then this was our query, well, the dot product between them, so Q, K transpose, would be 0 because they're completely linearly independent. So here we would say, no, this word does not answer this question. It answers it as a no. But for example, let's say the word deposited and the word bank, and our question is it related to money? So the answer is yes. So they might be heavily overlapping, okay? Something like this. And maybe our dot product between them would be something high, like 0.9, okay? Or 1 if they're completely overlapping. So you can see kind of where they fit onto this key query space after they're translated, and we ask how similar are they to each other. That's how we answer yes to a query. How we answer no to a query, well, they're completely unrelated and facing different dimensions. And then we apply some kind of scaling. It's mostly for numerical stability. And then we apply some softmax. So when we apply softmax, now this scales everything and it makes it a probability distribution. After we get kind of this matrix, which is a probability distribution that sums to 1, we apply this vector, which is a linear transformation based on, so for example, okay, so this value also accompanies each query key pair. So in our query key pair that I gave as an example was asking, is this related to money? The V says if it is related to money, it should change in the money direction, right? So this V also accompanies this key in query. If we have a different key in query that asks, is this word associated with music? Then our V vector would add a linear transformation to the original word embedding that changes it into the music direction. I'll explain more. I have some kind of more kind of pictures of that later on. That's kind of a theme here. Is I'm going to keep repeating the same thing multiple times until it completely makes sense to you. Because that's basically what learning is you just keep repeating the same thing a gazillion times, and then eventually it just like clicks in your head. So the two most commonly used, maybe I didn't, oh yeah, okay. In practice, we compute the attention function on a set of queries simultaneously packed together into a matrix Q. So now we say, even though in my example I gave you an example of one key query and V kind of tuple or like triplet together, a pair which was asking one question, it was answering that one question, and then there was a linear transformation V which said if that question was answered yes, this is how much the embedding value should be moved. But actually we have a group of these keys and questions, so that's represented with this capital Q. It's a bunch of different questions that you're asking, and we kind of apply it all together so that it's more efficient. The keys and values are packed together into matrices K and V. We compute the matrix of outputs as, again, the attention is calculated as, first we take the dot product between the queries and the keys. So we're saying if the dot product means that if the question is answered yes, then it will result in a high number when we take the dot product. If the query is answered no, then the dot product will be close to 0. And then we take the softmax to make sure it's all distributed from 0 to 1. So now we have a probability distribution for all the keys and queries. And then we apply the transformation saying, you know, if this in fact did answer the question as a yes, then we'll apply this transformation to the word embedding. The two most commonly used attention, and then I also want to notice that this is kind of like a weighting onto the V, right? So this kind of gives a weighting of how much, so each linear transformation is ready and we have the transformation for what it should be. But if the query was answered as 0, then 0 times V means it won't be applied. If the question was answered as a 1, then that transformation will be applied. The most commonly used attention functions are additive attention and dot product multiplicative attention. Dot product attention is identical to our algorithm, except for the scaling factor. Okay, so basically this is dot product attention, they added the scaling factor. Additive attention computes the compatibility function using a feed-forward network and a single hidden layer. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. While the two are similar theoretically, dot product detention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. So they're saying sometimes there's something called additive attention, which is not what we're doing in this case. In this case, we're just doing a regular dot product detention, which is basically after you've mapped your word embeddings into key and query space, you just take the dot product to figure out if the keys and queries attend to each other or not. There's another one called additive attention, which basically uses a feed-forward network with a single layer to calculate this kind of attention function. However, we don't need an extra neural network, so we're actually choosing the more simple option for computational reasons. While for small values of decay, the two mechanisms perform similarly, additive attention outperforms dot product attention when scaling for larger values of decay. We suspect that for large values of decay, the dot product grows large in magnitude, pushing the softmax into regions where it's extremely small gradients. To counteract this effect, we scale the dot product by 1 over decay. So they're saying that because we have this Q and this K are huge dimensional matrices. So for example, this is kind of what Q would look like, and this is kind of what K would look like, and then this DK would maybe be really large. Well, when we do this kind of softmax, what we're doing is softmax, we're adding up all of the, I think it's either the columns or the rows. I don't know if I drew it here. But we're adding up all the values in the columns and the rows, and when we have a higher dimensional space, it can add to a really high number. So they added this normalization term that divides that high number by 1 over dk. Okay, and so it's just like a scaling factor. So if the dimension is high, it will be 1 over a high number. That way, when we take the sum, it'll divide it by a higher number, and it'll make the value smaller. Okay, and then let's have, we're going to read about multi-head attention. Oh wait, let me see. Do we need to read about multi-head attention? Or should I go through the notebook first? Okay, yeah. Let's go through the notebook. Okay. So let's review this kind of what we learned. So we have this equation now for attention. And again, this entire part that we talked about is a weighting of sorts. It says weighting of how much each word affects the other. And then we have this V, which is a linear transformation of if this word does answer the specific key query question, then we should apply this specific transformation to the word embedding. If a specific word were to affect a word, if a key were to answer a query, how much would it change that word's meaning? Okay, so that's kind of the bread and butter of this. So take a step and really try to process this. Again, I'm going to pound it into your head for the next few minutes, but really just take a second to think about this, because this is kind of the most important part, this equation here in this entire paper. I wrote this is dot product attention, except it's scaled by this term, 1 over dk. Honestly, we could just kind of forget about it for comprehension reasons. It is something that we actually do need so that the values are numerically stable. So at large values of dk, the dot products grow large because they add many dimensional values, pushing the softmax function into regions where it has very small gradients. To counteract this, we do this. So recall softmax. Here I wrote like a little explanation of it. Softmax is the exponent of a value divided by the sum of all the other values in a column. This could be a very, very large value. When we calculate the derivative of it, which is used for the gradient calculation in backpropagation, well, when we take the derivative of this is kind of what it simplifies to, or this, depending on if we're on the current value, or if this, we're on a different value, if that makes sense. So I wrote it here as if I is equal to j, so that means is it that value that led to the next one, or is it another one? So in this case, we have the softmax, which is a small number, 1 minus a small number, so it's just a small number times 1. So then we have a very small number. So here our derivative would be small. And then here also we'd have a small number times a small number, so our derivative would be small. And it says it'll pushing the softmax functions into regions where the gradients get really small. So we can see, because the sum is in the denominator of the softmax calculation, any value where the denominator is really large compared to the numerator becomes a very small number. So something over a really large number is a really small number because it's divided into many, many different sections. And then we have to look at the gradients, because that's really what we're interested for backpropagation. Softmax, we kind of have this softmax times softmax, where if the softmax is a very low value, then the derivative will be very low and will have very low gradients. And when we try to train the model and we do gradient descent, it'll be very, very tiny steps and we'll basically get nowhere. So that's why we have to add this normalization term here. This normalization term will shrink the value of the softmax, and it will make it so that the derivative does not kind of vanish. Okay, so back to attention. That was a little kind of segue, or not segue, tangent. The key tokens are, the query tokens are brought into key query space with this vector WQ. So we have some kind of some kind of mapping matrix, WQ, which maps the word embeddings into some query space. Then we apply to the exact same words, the word embeddings, we apply this this WK matrix. Okay, so we have some words. Let's just call it V. It's a bunch of different words. This is I. This is love. This is cats. Okay? We multiply each one of these by a query, a key. So multiply, so it's V times, or actually, since it's matrix multiplication, I'm going to write it this way. This makes more sense matrix-wise. So again, when you apply a matrix, the matrix is written on the left side of a vector. So we transform all the word vectors into query space, into key space, and then one more transformation into this kind of V space, which is how much the word should shift. DK is the dimension of the key and query space, so it's different than the input word embeddings. Okay, so again, think of it as asking a question, query, and then answering a question, the key. For example, I love learning about machine learning. Let's say we ask a question, does the word have a word before it describing positive feelings of admiration or love? So that's our question. I know it's very specific, but this is kind of how it works, okay? So that's our first question, is does the word have a word before it or after it, depending on if it's masked or not. I really shouldn't have written this before. That describes it in a positive light, or feelings of admiration or love. Well, for the word machine that I used as an example, it'll ask this question, so we'll transform it with the query, and then all of these words will also be translated with the K, the WK. So I know I wrote K here, but it's actually WK for all of these. So we multiply each one of these words by WK, and then machine is multiplied by WQ. And then we take the dot product, and depending on if it's a high value or it's 0, that will say either yes for a high value and no for 0. So for example, machine, about. About, no, it did not answer yes to this question. Learning, no. Love, yeah, the word love is describing machine, so it is representing positive feelings of admiration, love. So this would answer yes to it. Let's move on to our next question. Is the word being used in an educational context? So again, we're using the example of machine. So first we would take the word embedding for machine. We would transform it with this WQ matrix, which will take it from the word embedding space into query space. And then all the other words will also be translated by this WK, which takes it from the word embedding space into the key query space, in this case answering the question instead of asking the question. And then we take the dot product between them, and that'll represent if it's a yes or no, or maybe it could even be a maybe if it's somewhere in between. So the question is the word being used in an educational context? Well, in this case, is about making the word machine educational in an educational context? No. Is the word learning affecting the meaning of machine to make it in a more educational context? Yeah, it is. We're learning machine learning. So, it's a more educational kind of use of the word machine. It's not maybe like a robot machine, or like a robo vacuum or something like that. Okay, so in this case, it would answer yes to the query. The word love. The word love is not using the word machine in an educational context. It did change its value into kind of a love or admiration context, but it did not change it in this case for the educational context. The word I, it did not change its value into an educational context. So in this case, only the word learning answered yes to this query. So that means all the other values will not really transform the embedding of the word machine, but the V matrix that we got by applying WV, which corresponds to this key, query, and V kind of couplet, well, that's how much will translate the word embedding for the word machine. So now it's slightly more in the educational space. So some more pictorial examples that I made. So attention changes the token embeddings based on the tokens around it. So for example, the sentence, I love learning about machine learning. That's our input sentence. First, it goes into some kind of embedding matrix, which takes the words and maps them into some higher dimensional space, specifically 512 different dimensions. And we're going to represent it by E1, E2, E3, E4, E5, E6. Then we apply this attention mechanism, where we let all the words around it affect the meaning of each word using this question answer, and then if it's answered yes, then we'll translate it by this much kind of mechanism. And then we have the output, which I labeled here as E hat, which represents the word embeddings after they've been transformed. So how do we do it? Well, we take a deeper look. This is what happens. We have some kind of format of storing all of our words. So again, since this dimension is D-context, that means each one of these rows is a different word. So this one would be I, this one would be love, machine, or learning about machine learning. And then D model is this. So this is just the different values that embedded into this higher dimensional space. We multiply it by this DQ value, which transforms it into some kind of query space. This, what is this WQ? It's actually learned. So we can initialize it to some random values to start off with, or just initialize it to 0. But through the training and the learning process, this is actually the part that we learn. So we are learning what questions to ask it how to answer the questions yes or no, and how to transform the values if the answer is yes. Okay, so we take all the words, we packed it into this, all the embedded words into this matrix. We transform it by multiplying it with this W matrix that maps it into a query space, and then we have Q, which is the questions that all the words are asking. And each word asks the same question. So the first question in our example was, does it have meaning of admiration or love? So now all the words are asking, do I have some kind of relationship to love or admiration? And that's this here. And then all the words are also, so this is the exact same matrix containing all the words. All the words are also mapped using this WK matrix into some kind of key space. And the key space, again, comes together as a pair with this query space and the V space. So they all come in a pair. So the key space is answering the query that it's associated with. So in this case, it's answering yes or no to am I affecting the meaning of this word based on feelings of love or admiration, okay? So this WK is being applied, and then we have some key space here. Then the words are also mapped by this WV here. Notice the difference here is this dimension here. So this is kind of the dimension that we get in the output. So the key query space is in DK dimension, and then this is kind of the dimension of the questions and the queries, the queries and the keys, so the questions and the answers. And then once it maps it into it, well, we have this D context is still constant, which means that this one is still associated with I, this one is still associated with love, the next one is still associated with learning, but it's kind of in this different dimensional space than we started off with. Notice how they all start off in this D model space, but after they're mapped into the key query space, then they end up into this DK space, which is smaller than the initial model space. But this value space is different than the key and query space, okay? So that's kind of just something to notice. Again, it doesn't really matter that much. Okay, so the transformation applied by WV is if this specific query is answered, what change would need to be applied in DV space to the tokens to modify their context. So this change is only in DV space. In order to be applied into the original word embeddings, we actually do also have to transform this into the model space, okay? But I think this was made smaller specifically for computational reasons so that it would run faster. And I think they'll say it eventually in the paper at some point. So again, the attention is calculated using this equation, okay? And now we have the query and the keys, the question and the answer, and we calculate the dot product. Notice that the K is transposed, so now we've flipped this dimension from being the context length and then times the DK dimension. Well, now it's actually flipped, so it's DK dimension times context length, and if we look, well, this DK will disappear, and we'll just have D context times D context at our output. So this dot product produces this attention matrix, and each value in the attention matrix means is kind of like one single value, a number, a scalar number that represents yes or no for if this word is answering this query or not. So notice that when we do the matrix operation, we do this value times this value, this value times this value, this. So we go down along this row and down this column, and we sum it all together into one value, okay? So we're saying this query multiplied by this key, and that's the dot product, where we take each coordinate and we multiply them together, and then we sum them together, and we get one single number value. And all of that is represented in kind of the first cell here in the attention matrix. So the first cell can be thought of how does the first word's query and the first word key line up? So does the first word's key answer the first word's query? If yes, then this will be a high number. If no, it'll be close to 0. And then we'll do it again between all of the words. So we'll do the first word and then the second word. And it's asking, does the second word answer yes to this query? And again, we take the dot product, so this time it's along the first row, second column, add it together, and then that'll be the second cell here, and it'll just be one number, ranging from 0 to 1 usually is dot product, if it's normalized, okay? And after that, so after we have the attention mechanism, and again, it's how all the other words answer the query for, okay, well, so this arrow is pointing just to the first row. So this first row tells us for word 1, how do all the other words answer this query for the first word or the first token. And then the second one will be for the second token, and so on. Then softmax is applied to the rows. Okay, so like this, softmax of each one of these blocks. Why? Because this is corresponding to the first word, okay? And we want this to scale to sum from 0 to 1, because we're saying how much does the first word answer this query? How much does the second word answer this query? How much does the third word answer this query? And we want it to sum to 1, so it's kind of a probability distribution, okay? So we softmax the rows. So for each word, the attention for this query by all the other words sums up to 1. Okay? And then I'm showing it here. So we take the softmax of each one of these rows. Next, we use this attention matrix as a weighting to determine how much each V vector should be added to the word's context. So we take this attention vector, we multiply it by this G vector, and we get the sum of all the V vectors for that word. So let's kind of think about what's happening. So we take this, how much this V1 should attend to one word, and we multiply it by all of these different V's. Okay, let's take a second and really think about what's happening here, because here you can see that it's actually the sum of the V's. So why is it the sum? Okay, so this first block represents how much the first translation would occur if the first key in query answered yes. The second one is how much the translation would be if the second question and answer answered yes, and so on, okay? But the first word here, the first kind of block here, is the attention between the first word and the second word. So we're multiplying this with the first dimension of the first key in query answering yes. And then we're kind of stepping to the side. We're saying if the second word answered, then how much would it be translated in the first dimension, okay? And then we kind of go so on. So we're moving through all the words, but all in the first dimension. So this little square will result from that calculation. And it tells us if all of these attend, this is how much the first dimension should be changed. So it's actually a sum of all the different changes in the first dimension. And then again in the second one. So we're sliding all of these of how each of them affect the first word in the first dimension. So this one here is how much is the first word embedding 1 added to it. So think of it like a change, delta E1. The second one is delta E2. And remember this E was mentioned here. It's representing the embedding vector, okay? So since we have the sum, this entire column is how much the first word is affected. This entire column is how much the second word is affected. And here we're asking many different questions. So it's not just one question. We're asking the first question, which is represented in the first row. This second row represents the second question. But since we're kind of going through it, and I encourage you to stop this video and really do the calculation on your own to really see why it's a sum. But if you actually do the calculation, you see that as we sum along this, the first box here is the sum of how much the first word changes in the first dimension for all of the keys and queries. We do it again, but now the second column here, well, we slide along the second column because it's the second dimension, and we're summing it for all the keys and queries, how all the keys and queries affect the first word. And that's how we get the second dimension here, okay? And so on. So this kind of output is a sum of all the translations, all the questions and answers we asked for the first word. That's the first row. The second one is how much translation should we add to the second word for all the different questions and answers we asked here, okay? So it kind of squishes it together, and now we have this transformation vector. I tried to write it down as this. This specific row is the sum of all v's to be added to the first word in DV space. This is important too, is we're still in DV space, we're not in model space. In order to add it to this embedding, we actually still need to do a transformation to move it outside of this DV space and into the embedding space, so we can just add it, because when we add stuff together, we have to make sure that the dimensions are the same. So that's where this one comes in, this W naught, and then that's our final transformation that's applied to the sum, just mapping it from DV space into D model space, which is the right dimension to be added into our word embeddings, since our word embeddings are D model length long, which is 512 different dimensions. But note that the sum of the V matrix is in DV space, which I just said. So it must be transformed by the matrix W naught or W0, which maps it from DV space to D model space. So now we actually have, I know I wrote it here as the delta embedding, but actually it's here, the delta embedding. So this is actually the delta embedding 1 for the first word. This one's the delta embedding 2, because now it's in the proper space, and now it could just be added on to all of these embeddings for the words. Okay, so I feel like I've explained a lot more than we've actually read, but that's okay, we can continue reading. Okay, so now that we've gone over this attention mechanism and how it's applied to all the tokens, let's continue reading on the multi-head attention. Now, basically what multi-head attention is instead of kind of doing this question and answering one time, so we're asking one question by all the words, and then all the words are answering one answer, and then all the words are transformed based on this question answer value triplet. So instead of doing this, we can optimize it by kind of doing something called multi-head attention, which is basically just stacking multiple questions all at once. So instead of just asking one pair of questions, we actually make this kind of a 3D matrix. This is kind of how it looks like. Multi-head attention. So we have this 3D matrix, and it basically just stacks the multi-head attention, so that we're actually, instead of asking just one question, each one of these blocks is asking a different question. So we can see this one corresponds to question 1, this one corresponds to question 2, and so on. Let's read that section first before we kind of go on to that. Multi-head attention. Instead of performing a single attention function with D-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with different learned linear projections to dk, dk, and dv dimensions respectively. So this dv and dk and dk correspond to the key query space, and this dv is kind of the smaller intermediate space where we have the v transformation, which is then mapped using the W0 or W0 matrix into D-model space. On each of these projected versions of the queries, keys, and values, we then perform an attention function in parallel, yielding dv dimensional the next page. Yielding dv dimensional output values. These are concatenated and once again projected, resulting in the final values as depicted in figure 2. Here is this famous figure 2. So basically this is just the attention mechanism where we have the queries and the keys. First they go through this multiplication, which is actually just a dot product. Then I guess they're scaled, and then optional masking depending on if it's masked attention or unmasked attention. Recall that the masked attention only happens in the decoder, not in the encoder. We go through softmax, so we make sure that it's a probability distribution distributed between 0 and 1, so that this matrix is multiplied with all the values in V using matrix multiplication, but it can be thought of as a weighting. So from 0 to 1, all of the vectors might affect the embedding by whatever the weighting of this attention matrix is. But then here, this is basically the same thing, but here it happens h times instead of just one question each, like kind of 3D layer here is asking a different question, and it has a different query, key, and value matrix associated with that question. Okay, so let's go to the next page and continue reading. So these concatenations are once again projected, resulting in the final values as depicted in figure 2. Multi-head attention follows the model to jointly attend to information from different representation subspaces at different positions, with a single attention head averaging inhibits this. Here's the equation that represents this concatenation. So we concatenate head 1 all the way to head H, and then we apply to this entire group of all the questions we asked in one round, which I think was 8. Yeah, it says here 8. Then we will apply this linear transformation that maps it from this dv space into the d-model space, and then it can be applied to the embeddings. And this is kind of the more efficient way. So each one of these heads asks a bunch of, or just one question, but we have a bunch of them. We have 8 questions being asked each time, and then we transform it and we apply it to the embeddings. So actually here in their kind of nomenclature, I guess, the Q here is the embedding, and the W is being applied to Q. But notice in my notes, it's just the embeddings. So this is just the embeddings, and it's the same for query, key, or value matrix calculations. But over here, they're Q, K, and V. In all cases represent the embedding, which I think is a bit of a silly way to represent this. But basically, this is a little bit counterintuitive for me. My kind of notation makes more sense to me. Okay, I honestly think this was maybe something, I don't know, unless I'm misinterpreting it, feel free to leave a comment down below, but I feel like this is not the best way to represent it. And then they list here the dimensions of all of the matrices, but again, I've already listed them here. So this WQ matrix is a real number of dimension d model times dk. Here is it depicted kind of in a more geometrical manner, which I think is slightly more intuitive, and its length d model dk. Same with this WK matrix that maps the embeddings into the key space. And again, it's written here to be d model times dk. This is kind of how it looks like. And then the last one is a real number, WV, which is d model dv. D model dv depicted here. And finally, the last learnable parameter is this one that maps the sum of all kind of the linear transformation to this kind of how much the embeddings have changed, so that it can be summed with the original embeddings. So that's kind of depicted here. Okay. In this work, we employ h equals 8 attention layers or heads. For each of these, we use dk is equal to dv is equal to d model over h is equal to 64. So even though they went through all of the trouble of making it seem like queries, keys, and keys have the same dimension, but it's different than the values, they actually just ended up making it the same. And it happens to be the d model, which is 512 divided by 8, 64. So the reason why they did that is because for the same computational cost that it would take to run one key question answer value operation on the original dimension of the model, which was 512, that's the d model 512. If we kept everything in d model, we could only ask one question. So for the time that it takes to ask one question in d model space, we can shrink down the dimension 8 times specifically, and for the same time we can ask 8 different questions. So we kind of get more bang for our buck computationally wise. So that's kind of why they picked this kind of way of determining the dimensions of the query, key, and value matrix. And due to the reduced dimension of each head, the total computation cost is similar to that of a single attention with full dimensionality. So that's exactly what I just said. Okay. Let's go through my notebook. Okay, so we went through this part. I went through this part. Let's go through this part. So, again, in summary, this was the equation of the tension, which I encourage you to work through on your own. It's implemented like so. Let E be the matrix containing all the word embeddings as input into the attention mechanism of size d context times d model. D context is the number of words we have in our context window. So for example, I love cats, that's 3 context window. 1, 2, 3, I love cats. That's a context window of 3. Multiplied by d model. D model is the dimension of our embedding space, which is 512. And then we have the 3 different matrices. So let WQ be the learned matrix mapping the word embeddings into query space with this kind of dimension. WK is the learned matrix mapping the words into key space, and WV is the learned matrix. Learned matrix is important because we're learning these, mapping the words to transformation in V space, represent changes based on their respective Q's and K's. This is learned alongside the WQ and WK of the dimension. So I think my grammar made no sense there, unfortunately, but basically this WV accompanies the WK and the WQ, the matrix mapping the embeddings into V space, accompanies the set of WK and WQ which map the embeddings into key and query space, and they show how much the word embedding is shifted in the direction if that key does answer that query. And then I kind of tried to draw it here a little bit. So we have our original embedding, and then we apply this WQ vector to our original embedding. So this is kind of the word in 3D space, but let's imagine it's 512D space. We apply this mapping into query space, and we get a question vector. And then we kind of do a similar thing. So here I just opened up the equation here. So the equation where Q is actually WQ applied to the embeddings. This K vector is WK applied to the embeddings, transposed. So this is actually kind of what happens in matrix form. This V vector is this WV applied to the embeddings. And this is kind of the sum at the end. Of course, this is actually missing the last one, which is the W naught vector, and matrix, and the W naught or W0 is the learned matrix mapping from DV space to model space. So once we apply the W naught matrix onto the sum of all the shifts in DV space, then we can actually get kind of a delta embedding, which is equal to this. So again, this is the exact same equation here, which is the attention equation that we see popping up all around this paper. And here it is. It's right here. The entire thing, exactly this, but now including this mapping back into model space, so that at the end we get a delta embedding here. Therefore, the delta E is added to the original word embeddings. So that's the original E's that we have here. This delta E is added to the original word embeddings and changes the embeddings based on the attention and context. So here is the original E, which is the exact same one that I drew here in our multi-dimensional space. In this case, again, it's only 3D, but imagine it in 512 dimensional space. It's kind of difficult. So the word is embedded. We add this delta E or change in E based on all the multiple questions we asked about it, the multiple questions we asked about it in the multi-head attention block. Specifically 8 questions we asked about it. 8 questions, 8 questions. We add it into the E, and then we have this new embedding pointing in a different direction. So this kind of pointing in a different direction represents that the meaning of the word has changed, even though it's the same word and originally it was mapped to this. For example, the word deposit or the word bank. Yeah, let's do the word bank. So for example, the word bank started pointing up this way, and let's say it was shifted in this direction. Maybe that direction is corresponding to the money or the finance direction. So after the linear transformation in this way, then we have it pointing this other direction. After the attention is dot producted and out of frame. After the dimension is dot product and soft maxed, this is now a decontext size matrix. So now I'm kind of just zooming in to the attention bit. So the attention bit is specifically kind of this part of it, only this part of it, excluding this. This is like the attention bit of it. So this is kind of what the attention looks like. Okay, so notice it's just this part of it, excluding the V, okay? And it tells us how much does each word attend to each other word. So how much does is the key query combination answered yes or no? So it's a decontext by decontext size. That means that each row and each column represents one of the words in the sequence. So for example, let's say our sentence is dogs are so cute. This entire column represents dogs. This entire column represents are so cute. And then same with the rows, dogs are so cute. And then the value at the intersection is how much each word attends to the other word, okay? Specifically, I think column-wise, row-wise is how much dog attends to dog, how much are attends to the word are, how much the word so changes the value of the word dog based on the specific key query value, how much the word cute changes the value of dog based on the specific key query value that we're asking in this specific case. So for example, let's say in this case we're asking cute is asking a question answered by dog, and the dot product between cute's q vector, because cute is asking the question, and dog's k vector is represented in this cell in the attention matrix. The matrix becomes a weighting for the V matrix. So since we add the attention matrix, or not add, but we multiply the attention matrix with the V matrix, we can think of it as this. The A matrix becomes a weighting for the V matrix, symbolizing how much the embedding should be changed and in which direction. So here's kind of an example. Question: do you describe an association with an animal? So for example, we have 3 different words here. We have the word so, the word cute, and the word dog. We apply the query matrix onto them, and we get it in key query space. So even though I only show query here, technically I'm also applying key, because I say here dog in K space. So this dog is a query. And then this is cute in Q space. And then here we can see when we calculate the dot product of how much does dog change the meaning of cute in association to an animal. Well, it's probably high because they're both animals. Specifically, dog is an animal. So if we're talking about dog earlier on in the sentence or at a different point in the sentence, well, we're likely that cute is being associated with an animal. So now, because we use the word dog, it might shift cute into the animal direction. So now the word cute is cute in an animal way, instead of maybe if you were to use it in a demeaning way, you know, oh, that's cute, you know, in that case, it's maybe like an insult word. And then if it was used in that context, then maybe it was shifted into some other dimension that was a not very nice dimension, or someone's being rude dimension, you know? The A matrix, in the A matrix, since the dot product between cute and dogs is equal to 1, that means that the query and the key value pair in this case was answered as a yes. The vector for how much the word dog should change, cute, will be weighed by a larger number. So now, after the attention mechanism, what we're really doing at this point in the operation, when we multiply the attention matrix with the value matrix, what we're really doing is for each kind of value here, we're multiplying the entire V dog vector. So that we have like the vector that shifts it based on the first question and answer, and V combination. We have how much is it changed if dog answers yes. So each one of these is multiplied by dog, because if we think about it, dog is attending to each one of these words. So here, dog attends to the word dog by whatever number is in the cell. In this case, the word dog attends to the word are by this number, and so on. So you can think of it as this value is a weighting added to this V dog, which is the first row. And then the second row, which is VR, is how much will the word be changed if R attends to it in this specific question answer pair. And in that case, the second column will be multiplied by the VR. In this case, you can think of it as a weighting on VR. Okay, what was my thought bubble? Okay, I wrote some thought bubble. I'm going to read it out loud to you. I can't really remember why I wrote this, but it says, thought bubble. The example given are misleading. I think I'm talking about my own examples. Notice there is one V vector representing a shift in the word's context for each word. So how does dog change a word? How does so change a word? And how does cute change a word? And I think I answered my own question here. The word dog might bring the context in an animal direction or in a pet direction. The word cute might bring the context in a positive, adorable direction. Since this is unique for V for each word or each query key pair, they would all be representing a different transformation on the word context. So I don't actually know what question I was asking here, unfortunately. Maybe I'll read it over again a few times and try to figure out what I was asking, because I'm quite confused. When the attention and V vectors are multiplied, it's the same as asking the sum of all V's applied to a specific word. So this I already kind of talked about. It's the exact same thing. I'll go back 2 pages ago here. Sorry, this one right here. So it's kind of this sum phenomenon, which I already discussed. Okay. And lastly, multi-head attention in my notes. Finally, we get here. So we can perform a single attention function with D model dimensions, or we can make the query key and DK and V of, okay, so here I'm just talking about dimensions, but it's when I read it out loud, it sounds a little crazy, but we can make the query key space of DK dimensions and the V space of DV dimensions, and apply each different key query and V transformation on the tokens, asking more questions about each attention block, but in a smaller, more compact space. So this is what I'm talking about, the computational benefit of shrinking it into the smaller key query V space instead of working in the model space. Each of the H attention blocks is performed in parallel. That's always good when we can parallelize a computation. It saves us some time. The output of all the change in V vectors is concatenated and projected back from DV to D model space and added to the word embeddings. Again, this is for multi-head attention, the little equation that I read out on the paper. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. So we concatenate the many different questions. So each head here is a different attention head, which asks a different question. And then we concatenate together at the end after we've measured the attention and we've measured how much, not measured, but calculated how much shift in DV space is required. And then we apply this matrix to map it from DV space to D model space so we can add it to our word embeddings. And this is kind of what each attention, each head is an attention block. And then again, talking about the model dimensionality. Okay. In the paper, they use H is equal to 8, which means in each multi-head attention, they ask 8 questions. The total computation cost is similar. This is what I've talked about. There are 3 types of attention implemented in transformers. Okay, so in the encoder, in the decoder, and this intersection between the encoder and decoder. So specifically, there's one attention, multi-head attention in the encoder. There's one multi-head attention in the encoder. There's one multi-head attention in the decoder on its own. This is self-attention, so that means we're calculating the attention between the words and the words themselves again. And then this cross-attention is between the different words. So the words in language A and the words in language B are being attended to. So that's the third different attention head. So first, there's one in the encoder, one in the decoder, and then the cross attention here. So recall that the one in the encoder is not masked, meaning later words can affect earlier words. The one in the decoder, the first one, is masked, meaning we mask out all the words that come after it, and only the words before it can affect a certain word. And then finally we have the one where they intersect, and this one is also not masked. So later words can affect the meaning of earlier words. Okay. My papers are all out of order now. Let me try to organize this a bit. I think I was at this spot. Okay, so let's read about that here. Is the applications of attention in our model. The transformer uses multi-head attention in 3 different ways. So again, that's the 3 different ones that I just mentioned. Here. So the encoder attention, the decoder attention, and then the intersection of the two, technically at the end of the decoder. So the first one is the encoder-decoder attention. So that's the one at the intersection between the encoder and the decoder. It says, in the encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory key and values come from the output of the encoder. So you see how this feeds into here? So that's the decoder, and that's the queries, queues. Okay? And then these two are the key and values. So the answer to the corresponding to the queries, and if the answer is yes, so we'll mark that as a K, and if the answer is yes, we have the accompanying V vector. And those are obtained from the output of the encoder. So that means in the decoder, that's where the questions are being asked, and they're being answered by the encoder. And intuitively this makes sense, because if we have a half-translated sentence already, for example, j'aime les blank, you would want all these words to ask questions to the English version that it's trying to translate, to try to figure out kind of what's going on here and what it's trying to translate. And based on if these answer yes or no to the questions, we also have some V matrix that transforms it. So we have in the encoder-decoder attention layers, the queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. So notice how they said all positions, meaning that it's not masked. This mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models such as, and then they cite some papers. The encoder, so now we're on to the second one in the encoder. That's this one, which is a non-masked multi-head self-attention. In the encoder, we contain self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. That means that the inputs here, see how we have 3 inputs? Well, we have keys, queries, and values, and they all come from the word embeddings of the language kind of being translated. So in this case, it's I love cats in English. Okay, so it says the encoder contains self-intention layers. In a self-intention layer, all the keys, values, and queries come from the same place. In this case, the output of the previous layer in each encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. So that means it's not masked, since each position in the encoder can attend to all positions in the previous layer of the encoder. Then we're going to move on. The third paragraph is the attention mechanism in the decoder. So the attention mechanism in the decoder is right here. It's the masked self-attention. So the only difference between the one that we just read in the encoder versus the decoder is that this one is masked. So it says, similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the encoder up to and including that position, aka it's masked. Only the words before it can affect the value of the current word. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of a scaled dot product attention by masking out, aka setting to negative infinity, all values in the input of the softmax which correspond to illegal connections. See figure 2. Okay, so what that means is why they set it to negative infinity. Well, okay, let's first see this kind of multi-head attention. So this entire page mimics the exact same operation that I showed for single head attention. In this page, this is kind of a single head attention. So that is all reflected here. So instead of having our query look like this, well, now it's 3-dimensional because we're asking multiple questions. Same with multiple answers to these questions, and then multiple transformations based on if the answer is yes or no. Okay, and then we have, so here I wrote kind of the equation. So we do the dot product, we scale it, we softmax it, and that gives us our attention block. So that's the query dotted by the keys, multiplied by the scaling, softmaxed, and that gives us our attention block. And then we take that attention block, multiply it by the V's, which is the transformations in the dimension space, and we apply it, and then we get kind of this dV. So it's the shift in the embeddings in dV space, and again it's 3-dimensional, but we actually concatenate it, which means that we unravel it. So now it kind of becomes this long 2D vector. So you see how it was 3D, where each this kind of third dimension as I go along here in the slice domain is a different question being asked and answered. But then we unravel it and it kind of looks like this. And then we apply the corresponding W matrix. So keep in mind that each W naught matrix is specific to each query and key pair. So that's why we have to kind of stack the W naught matrices as well, which transform the dV space into E space. Okay, and then finally we kind of get this one decontext by D-model matrix that corresponds to the linear transformation for each one of the word embeddings. Okay, so now we get into this masked. So in the case of masked attention, we only want attention weighting between words before it and the word itself, okay? So how is this implemented? Before the softmax, before we apply the softmax to the dot product, before the softmax, unwanted values are set to negative infinity. So the matrix is multiplied by a matrix that looks like this. It's a diagonal matrix where all the values in this quadrant are set to negative infinity, and then all the values here are set to 0. This is kind of how it looks. Why is it set to negative infinity? Well, if you look at the softmax equation, we measure the softmax, I think it was across the rows, right? So when we take the exponent of a negative infinity number, well, exponent looks like this. So what is it at negative infinity? Well, it's basically 0. So when we take the exponent of all of these negative infinities, it just goes to 0. So that's really, oh, here's my plot of the exponent function. So it kind of explodes with larger numbers, but at smaller numbers, which is somewhere here, it just approaches 0. So the softmax, of negative infinity is, here it is, exponent to negative infinity over the sum across the entire row. So this is just going to be 0 in the numerator. The denominator, there's going to be at least one value that's not 0. So it'll be around 0 for that value. Okay. This is implemented by adding the M matrix to the attention before the softmax. Right, so we basically just add this to our attention matrix here, and the negative infinities will just dominate, and it'll make this entire quadrant, if it's the masked attention, it'll just make it negative infinity. So only these values remain. That means there's just one pair of queries and keys for only the words before it. Okay, so I think we'll stop there. The next part is positional encoding, but we kind of talked about the main things here. So let's go kind of through what we just talked about. Okay. My pages are out of control. Look at third page, second page, fourth page, fifth page, sixth page. Oh, first page. I lost my first page. So let's rewind. We went through the abstract. We talked about the introduction, which talks about recursive neural networks, convolutional neural networks. We talked about the background of those, and then we got into the actual transformer model. We talked about, it's a little messy, but we talked about the encoder, the decoder architecture. We talked about them individually before even looking at attention. We said how these blocks are actually stacked up on each other. How many times was it? 6 times? And then we started talking about attention. I gave you an example of attention. I love this little picture that I made. Oh, wrong page. This picture that I made of attention. Let's go to single head attention. So that's the single head attention here, okay? The queries, the keys, the values, showing all of it in matrix form. Take a second and pause at this page and really read that through and so-call that in with the proper matrix multiplications and the proper dimensions, and ask yourself, does all of this make sense? And then we talked about the attention equation here. We talked about how we apply the queries, keys, values into the word embeddings. We dot product the queries and the keys. and then we softmax it and apply it as a weighting to the V's. The V is the transformation that's actually applied to the word embeddings. Then we talked about multi-head attention. So multi-head attention here. So basically it's the exact same thing, but now it becomes 3D because we ask each question, specifically 8 different questions at the same time. So again, we apply the query, which is the question, the key, which is the answer to the query, and the V, which is the linear transformation that corresponds to the set of query, key, and transformation V. Okay, multi-head attention. Oh no, I'm messing up my papers again. Multi-head attention. We reviewed the different types of attention, the fact that they're masked. Why are they masked? How are they masked? They're only masked in the decoder because autoregression makes it efficient for training. They're masked by adding that matrix with the negative infinities on this quadrant. So this way only, so this is how the first value attends to the first word. This is how the second word attends to the first word. Well, it doesn't because the second word comes after it. So we're masking this out. How does the third word attend to the first word in masked attention? Again, it doesn't because the third word comes after the first word. Here, the second word is being attended to how much by the first word. That's allowed. The second word can be attended to by itself, the second word, that's allowed. But it can't be attended to by the third word. Okay, so we add this. We add the negative infinities. Why? Because when we apply the softmax, the exponent of negative infinity goes to 0. So the softmax for this part will be 0. And if it's 0, that V weighting will also go, the V transformation will also go to 0 at that spot. So no transformation will be applied. Okay. We talked about the 3 different types of attention in the architecture. The attention, which is self-attention, non-masked in the encoder. In the decoder, it's masked self-attention. And then we have the intersection of the two where the output from the encoder joins from the output of the last attention block in the decoder. They join forces and we have cross attention. It's not masked, so later tokens can influence earlier tokens. And that's the 3 different types of attention. So I hope that you enjoyed that little demo. If you are still awake, congratulations to making it to the end of this video. You now have a much better grasp of attention is all you need. The paper, the kind of founding paper that implemented transformers for the first time ever with only kind of attention, foregoing recursive neural networks and convolution. If you enjoyed this video, please thumbs up, share, and subscribe. And please leave a comment. Leave a comment down below. And tell me what you would like to see, what you liked about this video, what you didn't like. And I'm so curious because I love the concept of this YouTube channel. I love teaching you guys about math and science and machine learning and artificial intelligence. And I hope to come back to you with many more videos. Okay, have a good evening, have a good sleep. Ciao, ciao.